Close your eyes and imagine the very first moment. Not the moment you were born, or when the earth formed, or even when the first stars began to shine. Imagine the very first heartbeat of everything that has ever existed. In that instant, something extraordinary happened. The universe didn't create just one kind of matter. It created two. Like a cosmic mirror reflecting itself, every single particle that came into being had a perfect twin. These twins were identical in almost every way, yet fundamentally opposite. Think of it like this. Imagine you're looking at yourself in a perfectly still lake. The reflection shows your face, your eyes, your smile. Everything is exactly the same, yet something feels different. The reflection is you, but it's also not you. It exists in a world that mirrors yours completely. This is what happened when the universe was born. For every electron that sparkled into existence, an anti-electron appeared beside it. For every proton that began its journey through space and time, an antiproton took its first breath. The cosmos became a dance floor where particles and their perfect opposites waltzed together in the darkness. Scientists call this shadow world antimatter. But that name makes it sound scary or dangerous. It's not. Antimatter is simply matter's quiet twin. It behaves the same way. It follows the same rules. It even dreams the same dreams, if particles could dream. The only difference is in something we call charge. You know how magnets have a north pole and a south pole. How they can either attract each other or push each other away. Particles work like tiny magnets too. An electron carries a negative charge, like the south pole of a magnet. Its twin, the positron, carries a positive charge, like the north pole. But here's where the story becomes beautiful and strange. When these perfect twins meet, something magical happens. They don't fight or compete. Instead, they embrace. And in that embrace, they both disappear completely. Not disappear like a magician's trick, where something is hidden but still there. They truly vanish, transforming into pure light and energy. It's as if two dancers, spinning toward each other across a ballroom, meet in the center and become music itself. This process has a scientific name, annihilation. But don't let that word frighten you. It sounds violent, but it's actually the most peaceful thing in the universe. When matter and antimatter meet, they don't destroy each other in anger. They transform into something new together. They become photons, particles of light that carry their combined energy out into the cosmos. Imagine two raindrops rolling down a window. They travel separate paths, each carrying their own small piece of the storm. Then they touch. In that moment, they become one larger drop, carrying the memory of both. Matter and antimatter do something similar, except instead of becoming water, they become light. In the very beginning, the universe was filled with both kinds of particles. Matter and antimatter existed in equal amounts, like two perfectly balanced scales. The cosmos was a soup of particles and antiparticles, all swimming together in the hot, dense space that was everything and everywhere. You might wonder, if particles and antiparticles always annihilate when they meet, how did anything survive? How are you here, made of matter, reading these words? How do stars exist? How does Earth exist? How does anything exist at all? This is one of the deepest mysteries in science. If the universe started with equal amounts of matter and antimatter, and if they always destroy each other when they meet, then everything should have turned into light. The universe should be empty except for photons traveling through the darkness. But something saved us. Something tipped the cosmic scales just slightly in favor of matter. For every billion particles of antimatter, there were 1,000,001,000 particles of matter. That tiny difference, just one extra particle out of every billion, made all the difference. When the universe cooled enough for particles to find each other, something extraordinary happened. The billion antimatter particles found their billion matter partners and annihilated into light. But that one extra particle of matter from each group had no partner to dance with. It remained alone. Those lonely particles are everything you see around you. Your body. The air you breathe. The earth beneath your feet. The sun that warms your face. Every star in the night sky. We are all made from the survivors of that cosmic dance, the matter that had no antimatter partner to embrace. But this raises another question. Where did antimatter go? Did it simply vanish from the universe forever? The answer might surprise you. Antimatter didn't disappear completely. It still exists, but only in tiny amounts. It's created in the hearts of stars, in the depths of space, and even in storms on Earth. Sometimes, when cosmic rays, particles traveling at incredible speeds from distant stars, crash into our atmosphere, they create brief flashes of antimatter. Lightning bolts, those brilliant fingers of electricity that dance across storm clouds, can also birth antiparticles for the briefest moment. Scientists have learned to create antimatter in their laboratories too. They use giant machines called particle accelerators, think of them as cosmic particle racetracks, to slam particles together at enormous speeds. In those collisions, energy transforms back into both matter and antimatter, just like in the early universe. But creating antimatter is incredibly difficult. The amount that scientists have made in all of human history would barely be enough to light a small bulb for a few seconds. Antimatter is precious beyond imagination, more valuable than diamonds, gold, or any treasure ever discovered. This rarity makes antimatter feel mysterious and distant. But in truth, it's part of the same story that created you. You exist because of a cosmic accident, a tiny imbalance that occurred in the first moments of time. You are made from the matter that survived when its antimatter twins found each other and became light. Every atom in your body carries the memory of that ancient dance. Every breath you take, every heartbeat, every thought, all of it exists because the universe chose matter over antimatter by the smallest possible margin. As you drift toward sleep tonight, remember that you are part of this cosmic story. You are made from stardust and ancient particles, survivors of the universe's greatest transformation. And somewhere in the depths of space, antimatter still whispers its backwards songs, waiting for scientists to decode its mysteries and understand why the cosmic scales tipped in favor of the world you call home. Imagine you could shrink yourself down to the size of a dust mote. Then smaller still, until you're tinier than the smallest grain of sand. Keep shrinking until you're so small that you can walk inside an atom like entering a vast cathedral. In this microscopic world, you would see something beautiful and strange. Electrons dance around the atom center in patterns that look like clouds of possibility. They don't follow neat circular paths like planets around the sun. Instead, they exist as whispers of probability, appearing and disappearing like fireflies on a summer evening. Each electron carries a tiny spark of negative electric charge. Think of it as a raindrop that always falls downhill, following the pool of positive charges. This is the natural flow of the universe, negative charges moving toward positive ones, like rivers flowing toward the sea. But somewhere in this atomic dance, there exists a twin that moves differently. A twin that dreams backwards. Scientists discovered this twin almost by accident. In 1928, a physicist named Paul Dirac was working with equations that described how electrons behave. Mathematics is like a language that the universe speaks, and Dirac was trying to translate what it was saying about these tiny particles. His equations kept giving him two answers instead of one. It was like asking what is 2 plus 2, and getting both for and a negative for as correct responses. At first, this seemed impossible. How could there be two different kinds of electrons? Dirac realized that his mathematics was revealing a hidden truth. For every electron spinning clockwise, there could be another one spinning counterclockwise. For every particle moving forward through time, there could be another moving backward. His equations were describing both matter and its shadow twin, antimatter. The electron's twin became known as a positron. It looks almost identical to an electron, but it carries positive charge instead of negative. Imagine two dancers performing the same routine, but one moves to the left while the other moves to the right. They mirror each other perfectly, yet they're completely opposite. When you picture a positron, think of it as an electron that has learned to swim upstream. While normal electrons flow from negative to positive charges like water flowing downhill, positrons flow the opposite direction. They move from positive to negative charges, as if they're following a different set of rules entirely. This backwards nature makes positrons seem almost magical. In some ways, physicists describe them as electrons moving backward through time. Not literally, they don't age in reverse or remember the future. But mathematically, they behave as if time flows differently for them. Picture a movie of an electron moving through space. If you played that movie in reverse, the electron would appear to move backward along its path, and its negative charge would seem positive. This backwards electron is exactly what a positron looks like, an electron's reflection in time's mirror. The first positron was spotted in 1932, hiding in cosmic rays that shower Earth from outer space. It appeared as a tiny streak in a special detector, curving in the opposite direction from an electron in the same magnetic field. It was like finding a left-handed person in a world where everyone else was right-hand. Since then, scientists have discovered that every fundamental particle has an antiparticle twin. Protons have antiprotons. Neutrons have antineutrons. Even tiny particles called neutrinos, which barely interact with anything, have antineutrino partners that interact even less. These antiparticles don't just exist in cosmic rays or laboratory experiments. They're created naturally throughout the universe. In the core of stars, nuclear reactions produce both particles and antiparticles. In deep space, high-energy collisions between cosmic particles birth pairs of twins, one made of matter, one made of antimatter. The most beautiful thing about these particle pairs is how they're born. Energy can transform into matter, but it must create equal amounts of both kinds. It's like a cosmic law of balance. When a high-energy photon, a particle of light, transforms into matter, it becomes both an electron and a positron simultaneously. Think of it like a soap bubble splitting in two. The original bubble contains a certain amount of soap film. When it divides, each smaller bubble gets exactly half of that film. Similarly, when energy becomes matter, it splits equally between a particle and its antiparticle twin. This process happens everywhere around you, though usually at scales too small to notice. In hospital scanners, doctors use a technique that relies on positrons created inside your body. They inject you with a special sugar that contains unstable atoms. These atoms decay and release positrons, which immediately find electrons in your tissues. When the positrons meet electrons, they annihilate into pure light. This light carries information about where the meeting happened, creating detailed pictures of your bodies in a landscape. The backwards dreaming twins help doctors see inside you without ever making a cut. The story of positrons teaches us something profound about the universe's design. Nature doesn't just create particles, it creates balance. For every push, there's a pull. For every clockwise spin, there's a counterclockwise spin. For every electron flowing downstream, there's a positron swimming upstream. This balance extends beyond particles to the deepest principles of physics. The universe seems to be built on symmetries, patterns that remain unchanged when viewed from different perspectives. If you could flip the charge of every particle in the universe, changing positive to negative and negative to positive, the laws of physics would remain exactly the same. Yet this perfect symmetry raises a puzzling question. If particles and antiparticles are created in equal numbers, and if they annihilate whenever they meet, why do we live in a world made primarily of matter? Why aren't there antimatter planets, antimatter stars, and antimatter people living parallel lives in an antimatter galaxy? The answer to this mystery lies hidden in the earliest moments of the universe, when the cosmic scales tipped just slightly in matter's favor. But to understand that story, we must first explore what happens when these perfect twins actually meet, when electrons and positrons find each other in their eternal dance. As you settle into sleep, imagine the positrons created in distant stars, swimming upstream through space and time, carrying their backwards dreams toward an eventual meeting with matter's children. Picture two old friends who have been separated for a very long time. They've traveled different paths through life, experienced different joys and sorrows, but they've never forgotten each other. One day, they spot each other across a crowded room. Their eyes meet. They begin walking toward each other, slowly at first, then faster and faster. This is what happens when an electron and a positron find each other in the vast emptiness of space. They are old friends, twins born at the same moment from the same burst of energy. One carries negative charge, the other positive. They are identical in every way except for this single, crucial difference. As they approach each other, something magical begins to happen. The electron, with its negative charge, feels the pull of the positron's positive charge. It's like two magnets drawn together by invisible strings. The closer they get, the stronger the attraction becomes. But this isn't just any ordinary meeting. When matter and antimatter touch, they don't simply bounce off each other like billiard balls. They don't stick together like pieces of clay. Instead, they perform the most elegant disappearing act in the universe. In the moment of contact, both particles vanish completely. Not vanish like a magician's trick, where something is hidden but still exists somewhere. They truly cease to be particles at all. Instead, they transform into something entirely different, pure energy in the form of light. Scientists call this process annihilation, but the word sounds too harsh for what actually happens. It's more like a gentle metamorphosis. Think of two snowflakes landing on your warm palm. They don't fight each other or struggle. They simply melt into water, becoming something new while keeping the memory of what they were. The light that emerges from this meeting isn't ordinary light. It's made of high-energy photons called gamma rays. These photons carry exactly the same amount of energy that the electron and positron had when they existed as particles. Nothing is lost. Nothing is destroyed. Everything is simply transformed. Einstein taught us that matter and energy are two forms of the same thing. His famous equation, E=mc², tells us that even tiny amounts of matter contain enormous amounts of energy. When an electron and positron annihilate, they prove Einstein's insight in the most direct way possible. The energy released from just one electron meeting one positron is incredibly small by everyday standards. It wouldn't even warm a grain of sand by a measurable amount. But on the scale of atoms and particles, it's enormous. It's as if two tiny dewdrops contained the power of lightning bolts. This transformation happens faster than you can imagine. The entire process, from the moment the particles touch to the instant they become light, takes less than a billionth of a second. It's quicker than a hummingbird's heartbeat, faster than a flower opening to the sun. Yet in that impossibly brief moment, something profound occurs. Two pieces of matter that took 13 billion years to find each other across the cosmos share one final dance before becoming energy that will travel through space forever. The photons created in this meeting fly apart in opposite directions, like dancers spinning away from each other at the end of a performance. They carry equal amounts of energy, ensuring that the cosmic books remain perfectly balanced. For every bit of matter that disappears, an equivalent amount of energy appears. This process can work in reverse too. Under the right conditions, pure energy can transform into matter and antimatter. When a high-energy photon passes near an atomic nucleus, it can suddenly split into an electron-positron pair. It's like watching the annihilation process played backward, light becoming matter, energy taking physical form. This backwards transformation happens constantly throughout the universe. In the cores of massive stars, intense radiation creates electron-positron pairs that immediately find each other and annihilate again. It's a cosmic recycling program where matter becomes energy becomes matter in an endless cycle. Near black holes, where gravity bends space and time into impossible shapes, this process creates spectacular displays. Virtual particle pairs pop into existence from pure vacuum, and sometimes the intense gravitational field separates them before they can reunite. One particle falls into the black hole while its partner escapes, carrying away a tiny bit of the black hole's energy. Even in the seemingly empty space between stars, this transformation continues. Cosmic rays, high-energy particles streaming through the galaxy, collide with stray atoms and create brief fireworks of matter and antimatter. Most of these particles find their partners within moments and return to being light. On Earth, we've learned to harness this process for healing. In hospitals, doctors use machines called PET scanners that rely on electron-positron annihilation. They inject patients with a special sugar containing unstable atoms that produce positrons. When these positrons meet electrons in the body, they create flashes of light that reveal the inner workings of organs and tissues. The beauty of annihilation lies not in destruction, but in transformation. It shows us that the universe is fundamentally creative, always finding new ways to express the same underlying energy. Matter and antimatter are like two different languages describing the same story. When you watch a sunset, you're seeing light that began its journey in the sun's core, where matter and antimatter pairs dance their brief dance before becoming the photons that warm your face. Every rainbow contains colors born from transformations that echo the cosmic process of annihilation and creation. The gentle violence of particles becoming light reminds us that nothing in the universe is permanent in its form, yet everything is permanent in its essence. Energy cannot be created or destroyed, only transformed from one beautiful expression to another. As you drift toward sleep, consider this: the atoms in your body were once starlight, and someday they may become starlight again. You are part of an endless conversation between matter and energy, between form and formlessness, between being and becoming. In your dreams tonight, you might hear the whisper of distant annihilations, pairs of particles finding each other across the darkness and choosing to become light together. Their transformation echoes through space and time, carrying messages about the universe's deepest desire to balance every equation and answer every question. But these cosmic conversations raise new mysteries. If matter and antimatter are created in equal amounts and annihilate so readily, why does our universe contain so much more matter than antimatter? Imagine you could travel backward through time, past your childhood, past the formation of Earth, past the birth of the sun, past the emergence of the first stars. Keep traveling backward until you reach the very beginning, the first fraction of a second when everything began. In that moment, the universe was nothing like the gentle cosmos you see in tonight's sky. It was impossibly hot, denser than anything you can imagine, and smaller than the period at the end of this sentence. Everything that would ever exist was compressed into a space so tiny that atoms couldn't even form. This was the cosmic soup, a bubbling cauldron of pure energy where matter and antimatter were born together in perfect equality. There were no elements yet, no hydrogen or helium, no carbon or oxygen. Just energy transforming into particles and particles transforming back into energy in an endless, chaotic dance. Picture a pot of boiling water on the stove. Bubbles form and rise to the surface, only to pop and disappear. In the early universe, particles behaved like those bubbles. Pairs of electrons and positrons materialized from pure energy, existed for the briefest moment, then found each other and annihilated back into light. The temperature was so extreme that it measured trillions of degrees. At such heat, normal matter cannot exist. Even the nuclei of atoms would be torn apart instantly. Instead, the universe was filled with a plasma, a state of matter where particles exist as individual pieces, too hot and energetic to stick together. In this plasma, photons carried enormous amounts of energy. These weren't the gentle photons of starlight that you see today. They were gamma rays so powerful that they could create matter just by colliding with each other. When two high-energy photons met, they would transform into an electron-positron pair, adding more particles to the cosmic soup. But these newly created particles faced an immediate challenge. The universe was so dense with both matter and antimatter that any electron would quickly find a positron partner. They would annihilate within microseconds, returning their energy to the seething plasma around them. This created a remarkable equilibrium. Energy became matter, matter became energy, energy became matter again. The universe was like a cosmic recycling center where nothing stayed in one form for very long. Particles popped into existence and vanished faster than snowflakes melting on warm ground. As you listen to this story, remember that you are made from particles that survived this incredible chaos. Every atom in your body is a descendant of that primordial soup. You are literally made of stardust and ancient energy, transformed through billions of years into the complex, beautiful form you inhabit tonight. During these first moments, the universe was expanding and cooling rapidly. Think of a balloon being inflated. As it grows larger, the air inside becomes less dense and cooler. Similarly, as space itself stretched, the cosmic soup became less concentrated and began to cool down. This cooling was crucial. As the temperature dropped from trillions of degrees to merely billions, the balance between matter creation and annihilation began to shift. The photons carried less energy, making it harder for them to create new particle pairs. Meanwhile, existing particles had more time to find their antiparticle partners before new ones appeared. What happened next was the most important event in cosmic history. The Great Annihilation began. Electrons found positrons, protons found antiprotons, neutrons found antineutrons. In a cosmic fireworks display that lasted only seconds, almost all matter and antimatter in the universe found their perfect partners and transformed into light. The universe became flooded with photons from these annihilations. The energy released was so immense that it created a glow that filled all of space. This ancient light still exists today, stretched and cooled by billions of years of cosmic expansion. We call it the cosmic microwave background, the afterglow of creation itself. But here's the mystery that makes your existence possible. When the Great Annihilation was complete, when nearly every particle had found its antiparticle twin and become light, a tiny remnant of matter remained. For every billion pairs that annihilated, one lonely particle of matter survived with no antimatter partner to embrace. This leftover matter, less than 1 part in a billion of the original amount, became everything you see around you. Every star, every planet, every grain of sand, every living creature. You exist because of cosmic leftovers, because the universe had slightly more matter than antimatter in those first precious moments. Why this imbalance existed is one of the deepest puzzles in science. The universe seems to prefer symmetry and balance in all its laws. Equal amounts of matter and antimatter should have been created. Yet somehow, somewhere in that cosmic soup, the scales tipped ever so slightly in favor of matter. Scientists call this tiny preference baryogenesis, the birth of matter. It's as if the universe made the smallest possible bet on matter's survival and won everything because of it. Without this mysterious asymmetry, the cosmos would contain only light, traveling forever through empty space with no planets, no stars, no life to witness its journey. The particles that survived became the building blocks of complexity. As the universe continued cooling, protons and neutrons began sticking together to form the first atomic nuclei. Later, when temperatures dropped even further, electrons joined these nuclei to create the first atoms, mostly hydrogen and helium. These atoms eventually gathered into clouds, which collapsed under their own gravity to form the first stars. Inside these stellar furnaces, nuclear reactions created heavier elements like carbon, oxygen, and iron. When the stars died, they scattered these elements through space, where they became part of new stars, planets, and eventually, living beings. The cosmic archaeology of those first moments reveals that you are connected to the very beginning of time. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it traces back to that primordial soup where matter and antimatter dance their final dance. As you settle into sleep, remember that your existence is the result of an ancient mystery. You are here because the universe chose matter over antimatter by the narrowest of margins, leaving behind the cosmic ingredients that would someday become you. Tonight, as you dream, the cosmic microwave background continues to whisper the story of creation, carrying the echo of that great annihilation across billions of light-years, reminding the cosmos of its birth. But what exactly caused this mysterious preference for matter? What tipped the cosmic scales at the moment of creation? Picture a vast cosmic scale, perfectly balanced between two equal weights. On one side sits all the matter that could exist, every possible electron, proton, and neutron. On the other side sits all the antimatter, every positron, antiproton, and antineutron. In a perfectly symmetrical universe, these weights would be exactly equal, and the scale would remain level forever. But something mysterious happened in the first moments after the Big Bang. Someone, or something, placed one extra grain of sand on the matter side of the scale. Just one tiny grain among billions and billions of others. That single grain was enough to tip the cosmic balance and save the universe from eternal emptiness. This is the story of asymmetry, the beautiful imperfection that made your existence possible. In physics, symmetry usually rules everything. If you throw a ball up, gravity pulls it down with equal force. If you push against a wall, the wall pushes back just as hard. Nature loves balance, equality, and fairness. So why did the universe break its own rules at the moment of creation? Scientists have discovered several ways that nature shows a subtle preference for matter over antimatter. These preferences are so small that they're almost invisible, like a whisper in a thunderstorm. But in the extreme conditions of the early universe, even whispers could change everything. One of these preferences involves particles called kaons. Think of kaons as cosmic messengers that carry secrets about the difference between matter and antimatter. When kaons decay, when they break apart into smaller particles, they don't do it with perfect symmetry. They have a slight tendency to create more matter than antimatter, like a coin that's been bent ever so slightly to favor heads over tails. Another source of asymmetry comes from the way particles behave when you look at them in a mirror. In most cases, particles and their antimatter twins are perfect mirror images of each other. But sometimes, the mirror shows something slightly different. It's as if antimatter particles have a tiny flaw in their reflection, a cosmic smudge that makes them not quite identical to their matter twins. These imperfections seem so small that you might wonder how they could matter. But remember, the early universe was incredibly dense and hot. Tiny differences got amplified by the extreme conditions, like how a small pebble can start an avalanche on a mountainside. Imagine you're sorting through an enormous jar of mixed black and white beans. If there's even one extra white bean in the jar, and you keep randomly removing pairs of black and white beans, eventually you'll be left with just white beans. The early universe did something similar with matter and antimatter particles. During the first microsecond after the Big Bang, the universe was filled with equal numbers of particles and antiparticles, all bouncing around in the cosmic soup. But those tiny asymmetries meant that for every billion particle-antiparticle pairs, there was one extra particle of matter with no antimatter twin to dance with. As the universe cooled, the great annihilation began. Particles found their antiparticle partners and transformed into light. But when the cosmic dust settled, the lonely matter particles remained. These survivors, less than 1 part in a billion of the original amount, became everything you see around you. This process is called baryogenesis, which simply means the birth of matter. It's one of the greatest magic tricks in cosmic history. The universe made almost all of its matter and antimatter disappear, leaving behind just enough matter to build stars, planets, and people. But the mystery goes deeper than just counting particles. The asymmetry that saved us required very specific conditions to work. The universe had to be exactly the right temperature, exactly the right density, and the laws of physics had to be precisely tuned to allow matter's tiny advantage to grow into a cosmic victory. Think of it like growing a garden. You need the right soil, the right amount of water, the right temperature, and the right seeds. Change any one of these conditions, and your garden might fail completely. The universe needed its own perfect growing conditions to nurture the seeds of matter into the rich cosmos you inhabit today. Scientists call these requirements the Sakharov conditions, named after the physicist who first described them. Like a recipe for creating matter, these conditions tell us exactly what ingredients the early universe needed to break its own symmetry and choose matter over antimatter. The first ingredient is the ability to create or destroy matter itself. This might sound impossible, but in the extreme conditions of the early universe, the normal rules of matter conservation could be bent or broken. High-energy processes could create matter from pure energy or make matter disappear without leaving antimatter behind. The second ingredient is the violation of certain symmetries, those tiny preferences for matter over antimatter that we discussed earlier. Without these cosmic biases, matter and antimatter would have been created in exactly equal amounts, dooming the universe to emptiness. The third ingredient is time. The asymmetric processes had to happen when the universe was out of thermal equilibrium, when it was cooling and changing rapidly. If the universe had been in perfect balance, the tiny matter advantage would have been erased before it could grow into something significant. All three ingredients came together during the first fraction of a second after the Big Bang. It was a cosmic recipe that had to be followed perfectly, with precise timing and exact proportions. Too much or too little of any ingredient, and you wouldn't be here to hear this story. The remarkable thing is how finely tuned this process was. If the asymmetry had been slightly smaller, all matter and antimatter would have annihilated, leaving only light. If it had been slightly larger, the universe would have been filled with matter but might have collapsed back on itself before stars could form. Instead, the universe chose the perfect middle path, just enough asymmetry to ensure matter's survival, but not so much that cosmic evolution couldn't proceed. It's as if the cosmos knew exactly how to set the stage for complexity, beauty, and consciousness to emerge billions of years later. As you rest tonight, remember that your existence is the result of the universe's most delicate decision. Every atom in your body carries the memory of that ancient choice, the moment when the cosmos whispered a preference for matter and changed the course of everything forever. You are living proof that sometimes the smallest imbalances can have the greatest consequences. Your heartbeat echoes the rhythm of that primordial asymmetry, and your thoughts are made possible by the universe's subtle bias toward complexity over emptiness. The mystery of why this asymmetry exists continues to puzzle scientists today. Perhaps it holds clues about even deeper truths, about the nature of time, the structure of space, or the existence of dimensions beyond our everyday experience. But understanding this cosmic preference has led scientists to build remarkable machines deep underground, where they recreate the conditions of the early universe and hunt for the ghostly particles that hold the keys to creation itself. Imagine digging a tunnel so deep beneath the ground that you could fit a small city inside it. Now imagine making that tunnel perfectly circular, stretching for miles underground, lined with the most sophisticated machines ever built by human hands. This is the world of particle accelerators, underground cathedrals where scientists hunt for the universe's most elusive secrets. In these circular tunnels, particles race around at speeds that approach the speed of light itself. They travel faster than anything you can imagine, completing thousands of laps around the ring every single second. It's like watching invisible race cars that never need to slow down for curves. The largest of these machines is buried beneath the border between France and Switzerland. It's called the Large Hadron Collider, and its tunnel is so big that you could walk through it for hours without completing one full circle. Inside this tunnel, protons, the positive particles found in every atomic nucleus, are accelerated to incredible speeds using powerful magnetic fields. But these protons aren't racing alone. In the same tunnel, traveling in the opposite direction, another beam of protons speeds around the ring. The two beams pass each other thousands of times, like trains rushing past each other in the night. But at four special points around the circle, something magical happens. The beams are guided into head-on collisions. When protons crash into each other at these enormous speeds, they release energy equal to what existed in the first moments after the Big Bang. In these tiny, brilliant explosions, energy transforms back into matter and antimatter, just as it did in the primordial cosmic soup billions of years ago. Picture two soap bubbles colliding and bursting into dozens of smaller bubbles. When protons smash together, they break apart into showers of new particles. Some of these particles are made of ordinary matter, but others are made of antimatter, the ghostly twins that the universe chose to hide from us. Scientists surround these collision points with detectors that are marvels of human engineering. These detectors are like incredibly sophisticated cameras that can take pictures of events lasting less than a trillionth of a second. They capture the trails left by particles as they fly away from the collision, creating patterns that tell the story of what happened in that brief moment of creation. Among these trails, researchers look for the signatures of antimatter. Antiprotons curve in the opposite direction from protons when they pass through magnetic fields. Positrons spiral in patterns that mirror electrons but bend the other way. Each type of antiparticle leaves its own unique fingerprint in the detector, like footprints in cosmic sand. The hunt for antimatter is like archaeological work, but instead of digging through ancient ruins, scientists dig through the debris of particle collisions. They sift through millions of events, looking for the rare moments when antimatter particles are born and briefly dance through their detectors before vanishing again. Creating antimatter in these machines requires enormous amounts of energy. The electricity needed to run the Large Hadron Collider for 1 year could power a small city. Yet all of this energy produces only the tiniest amounts of antimatter, so little that it would take millions of years of continuous operation to create even a single gram. But quantity isn't the goal. Scientists aren't trying to make large amounts of antimatter. They're trying to understand how it behaves, how it differs from ordinary matter, and why the universe chose matter over antimatter in the first place. Each antiparticle created in these underground laboratories is precious beyond measure. Antiprotons are captured using magnetic fields and stored in special devices called penning traps. These traps use electricity and magnetism to hold individual antiparticles suspended in space, like invisible butterflies caught in bottles made of pure energy. In these traps, scientists can study antimatter for days or even weeks. They measure its properties with incredible precision, comparing every characteristic to those of ordinary matter particles. They want to know, are antiprotons exactly identical to protons except for their charge? Do antiatoms behave the same way as regular atoms? Do they respond to gravity the same way? The answers to these questions could unlock some of the universe's deepest mysteries. If antimatter behaves even slightly differently from matter in ways we haven't discovered yet, it might explain why the cosmic scales tipped in matter's favor during the first moments of creation. Some experiments go even further, attempting to create entire antiatoms. Scientists combine antiprotons with positrons to make antihydrogen, the antimatter version of the simplest atom. These antiatoms exist for only brief moments before they touch the walls of their container and annihilate, but in those moments, researchers can study how antimatter atoms absorb and emit light. The creation of antihydrogen is like capturing lightning in a bottle. It requires perfect timing, precise control of magnetic fields, and temperatures colder than the depths of space. When antiprotons and positrons finally combine, they form something that has never existed naturally on Earth, atoms made entirely of antimatter. Working with antimatter is one of the most challenging endeavors in science. Unlike ordinary matter, antimatter cannot touch any normal material without instantly annihilating. Scientists must manipulate it using only magnetic and electric fields, like trying to hold water using only your breath. The underground laboratories where this work happens are marvels of human ingenuity. Miles of superconducting magnets, cooled to temperatures colder than outer space, guide particles around their circular paths. Computer systems more powerful than entire cities' worth of laptops process the data from millions of collisions every second. These facilities represent humanity's attempt to recreate the conditions that existed when the universe was less than a second old. In doing so, we're not just studying antimatter, we're exploring the very nature of reality itself. We're asking questions about why we exist, why the universe chose complexity over emptiness, and what secrets might be hidden in the behavior of matter's ghostly twin. The particles created in these collisions carry information from the universe's birth. Like archaeologists studying ancient pottery shards, scientists examine the debris of these cosmic recreations to understand what happened in those first crucial moments when everything began. As you settle into sleep tonight, remember that deep beneath the Earth, machines hum quietly as they spin particles around underground circles, occasionally creating tiny sparks of antimatter that flicker into existence and vanish like cosmic fireflies. These experiments represent our species' deepest curiosity about existence itself. They are love letters written to the universe, asking it to reveal its secrets about the dance between matter and antimatter that makes all life possible. But antimatter doesn't exist only in these underground laboratories. High above our heads, cosmic rays rain down from space, carrying antiparticles born in the hearts of distant stars and the violent explosions of cosmic catastrophes. Look up at the sky on a clear night. Between you and the stars lies an invisible ocean of air, stretching upward for hundreds of miles until it finally dissolves into the vacuum of space. In this atmospheric ocean, something remarkable happens every moment of every day. Antimatter is being born and dying in silent fireworks displays that your eyes cannot see. High above the clouds, where the air becomes so thin that astronauts need spacesuits to breathe, cosmic rays arrive from the depths of space. These aren't rays of light like sunbeams streaming through your window. They're individual particles, protons, electrons, and atomic nuclei, traveling at speeds that approach the speed of light itself. These cosmic visitors have journeyed for millions or billions of years to reach our planet. Some were born in the violent explosions of dying stars called supernovas. Others were accelerated by the magnetic field surrounding black holes. A few may have traveled from galaxies so distant that their light takes billions of years to reach us. When these high-speed particles slam into Earth's atmosphere, they create cascades of new particles, like a cosmic billiard ball breaking apart a triangle of atoms. The collision releases so much energy that it's as if a tiny piece of the Big Bang happens again, 60 miles above your head. In these atmospheric collisions, energy transforms into matter and antimatter pairs, just as it did in the first moments of the universe. Electrons and positrons materialize from pure energy, existing for brief moments before finding each other and annihilating back into light. The sky above you is constantly flickering with these invisible births and deaths. Think of it like cosmic snow that melts before it can reach the ground. Billions of antiparticles are created in Earth's upper atmosphere every second, but most of them meet their matter twins within microseconds and transform into harmless photons that continue their journey toward space. But some positrons are luckier. They're born in just the right place, with just the right energy, to avoid immediate annihilation. These survivors spiral down through the atmosphere, guided by Earth's magnetic field like invisible butterflies following magnetic flower trails. As they descend, these positrons paint ghostly paths through the air. They are too small and too few to create visible light, but sensitive detectors can catch their faint signatures. Balloon-borne experiments float high above the clouds, equipped with instruments that can spot individual positrons as they dance through the thin air. Scientists have discovered that more positrons exist in Earth's atmosphere than simple cosmic ray collisions should produce. It's as if there's a hidden factory somewhere in space, manufacturing extra antimatter and sending it our way. The source of these excess positrons remains one of astronomy's gentle mysteries. Some researchers believe they come from dark matter, the invisible substance that makes up most of the universe but barely interacts with ordinary matter. If dark matter particles occasionally collide and annihilate each other, they might produce positrons as a byproduct. These antimatter messengers could be our first direct evidence of dark matter's existence. Others think the excess positrons come from pulsars, rapidly spinning neutron stars that sweep beams of particles across space like cosmic lighthouses. These stellar remnants are so dense that a teaspoon of their material would weigh as much as a mountain. Their powerful magnetic fields could accelerate particles to energies high enough to create abundant antimatter. Even Earth's weather contributes to the antimatter in our skies. During thunderstorms, the electrical fields become so intense that they can create matter-antimatter pairs from pure energy. Lightning bolts, those brilliant forks of electricity that illuminate storm clouds, are actually brief antimatter factories. When lightning strikes, it generates gamma rays energetic enough to transform into electron-positron pairs. These storm-born antiparticles exist for only moments before annihilating, but their brief lives add to the invisible antimatter snow falling gently through our atmosphere. The aurora, those shimmering curtains of green and blue light that dance near Earth's poles, also play a role in creating antimatter. When charged particles from the Sun interact with our planet's magnetic field, they create conditions similar to those in cosmic ray collisions. Some of these interactions produce positrons that spiral along magnetic field lines toward the poles. Imagine the aurora as Earth's way of painting with antimatter. Each ripple of colored light represents countless particles and antiparticles being born, living brief lives, and transforming back into photons. The beautiful displays you see from the ground are just the visible part of a much more complex antimatter light show happening in the upper atmosphere. Even satellites orbiting Earth encounter antimatter regularly. The detectors aboard these spacecraft record positron impacts like gentle cosmic raindrops. Astronauts living on the International Space Station pass through this invisible antimatter shower every day, though the particles are so few and so low in energy that they pose no danger. The antimatter created in Earth's atmosphere offers scientists a natural laboratory for studying these elusive particles. Unlike the antimatter created in underground particle accelerators, atmospheric positrons exist in the wild, free from the artificial conditions of human-made experiments. Studying these sky-borne antiparticles helps researchers understand how antimatter behaves in natural environments. They can observe how positrons interact with atoms in the air, how they're influenced by magnetic fields, and how long they survive before meeting their matter twins. This research has practical applications too. The same techniques used to detect atmospheric antimatter have led to advances in medical imaging. PET scanners in hospitals use similar principles to detect positrons inside the human body, helping doctors diagnose and treat diseases. The antimatter in our skies connects us to the broader universe in profound ways. Every positron created by a cosmic ray carries information about its origin, whether it came from a supernova explosion, a pulsar's magnetic field, or the annihilation of dark matter particles in a distant galaxy. By studying these atmospheric antiparticles, we're reading messages written in the language of cosmic rays. Each positron is like a letter in a vast cosmic alphabet, spelling out stories about stellar explosions, black hole physics, and the fundamental structure of space and time. As you lie in bed tonight, remember that this invisible antimatter dance continues above you. Cosmic rays arrive from across the galaxy, creating brief sparks of antiparticles that flicker and fade in the thin air above the clouds. Lightning bolts paint momentary antimatter brushstrokes across storm clouds. Aurora displays weave positrons into their ethereal light shows. This atmospheric antimatter connects your bedroom to the most violent and energetic processes in the universe, reminding you that even in the quietest moments, the cosmos continues its ancient dialogue between matter and its ghostly twin. But to truly understand and harness antimatter's potential, scientists must do more than simply observe these natural processes. They must learn to capture and control individual antiparticles with technology that approaches the realm of science fiction. Deep beneath a mountain in Switzerland, in laboratories carved from solid rock, scientists perform one of the most delicate acts in all of science. They catch individual antiprotons, particles so rare and precious that each one represents months of careful preparation and enormous amounts of energy. Imagine trying to catch a single raindrop from a thunderstorm, except the raindrop is invisible, moves at incredible speed, and will instantly disappear if it touches anything made of ordinary matter. This is the challenge facing researchers who work with antimatter every day. The journey begins in the same underground tunnels where protons race at nearly the speed of light. When these high-energy protons crash into a metal target, the collision creates a shower of particles, including a few precious antiprotons mixed among billions of other debris particles. Think of it like panning for gold in a rushing river. Among all the ordinary stones and sand, a few tiny flakes of gold hide, waiting to be discovered. The antiprotons are even rarer than gold. For every million particles created in the collision, only a handful are the antimatter treasures that scientists seek. The first challenge is separating antiprotons from all the other particles. Scientists use powerful magnetic fields that bend charged particles into curved paths. Since antiprotons carry the opposite charge from protons, they curve in the opposite direction. By carefully adjusting these magnetic fields, researchers can guide antiprotons along one path while sending all other particles elsewhere. But the antiprotons emerge from these collisions moving far too fast to be useful. They're like wild horses that need to be gradually tamed before they can be studied. Scientists use a process called cooling to slow them down, not by making them cold in temperature, but by reducing their speed and energy. This cooling happens in stages, like a series of gentle brakes applied to a runaway train. First, the antiprotons pass through clouds of electrons that absorb some of their energy. Then they encounter carefully tuned electromagnetic fields that further reduce their speed. Each step brings them closer to a state where they can be captured and held. Once slowed, the antiprotons enter the most remarkable prisons ever built, magnetic traps that exist only as patterns of electric and magnetic fields in empty space. These traps have no physical walls, no bars, no solid boundaries. Instead, they use invisible forces to create bottles made of pure energy. The most common type is called a penning trap, named after the scientist who invented it. Picture an invisible well made of magnetic fields, with steep walls that antiprotons cannot climb. At the bottom of this well, electric fields create a gentle bowl shape that keeps the antiprotons centered and prevents them from drifting away. In these ethereal cages, individual antiprotons can live for days, weeks, or even months. They orbit in precise patterns, like planets around an invisible sun, their motion governed entirely by the electromagnetic forces that hold them suspended in space. Scientists can control these trapped antiprotons with exquisite precision. By adjusting the trap's electric and magnetic fields, they can move individual particles around like microscopic marbles, bringing them together or keeping them apart as needed. It's like conducting an orchestra where each musician is a single antiparticle. The most ambitious experiments involve combining antiprotons with positrons to create antiatoms, complete atoms made entirely of antimatter. This process requires incredible patience and skill. The antiprotons and positrons must be brought together at exactly the right speeds and exactly the right moment for them to form stable bonds. Creating antihydrogen, the simplest antiatom, is like trying to thread a needle in the dark while riding a roller coaster. The antiprotons and positrons must be cooled to temperatures just a few degrees above absolute zero, the coldest temperature possible in the universe. At these frigid conditions, they move slowly enough to capture each other and form antiatoms. When antihydrogen finally forms, it exists in a precarious state. Unlike charged particles, which can be held by electric and magnetic fields, neutral antiatoms are much harder to trap. Scientists have developed special magnetic traps that can hold antiatoms, but only those in very specific energy states. The antiatoms that scientists create survive for only brief moments before they touch the walls of their container and annihilate. But in those precious seconds, researchers can study how antimatter atoms absorb and emit light, comparing their behavior to ordinary hydrogen atoms. These experiments test one of the most fundamental principles in physics, the idea that antimatter should behave exactly like matter, except for having opposite charge. If antihydrogen atoms emit light at even slightly different frequencies than hydrogen atoms, it could revolutionize our understanding of the universe. Working with trapped antimatter requires extraordinary precautions. The entire apparatus must be kept in a perfect vacuum, emptier than the space between planets. Even a single stray molecule of air could cause precious antiparticles to annihilate before scientists can study them. The magnetic traps themselves must be incredibly stable. The slightest vibration, the tiniest electrical fluctuation, could cause trapped antiparticles to escape and be lost forever. The laboratories where this work happens are isolated from subway trains, earthquakes, and even the footsteps of people walking overhead. Despite these challenges, scientists have made remarkable progress in taming antimatter. They've learned to store thousands of antiprotons for months at a time, creating the world's most valuable substance. A single gram of antiprotons would be worth more than the entire gross domestic product of most countries. But the goal isn't to create wealth, it's to unlock the secrets of existence itself. Each trapped antiproton is a messenger from the mirror universe that might have been. By studying how these particles behave, scientists hope to understand why the cosmic scales tipped in favor of matter billions of years ago. The antiprotons in their magnetic cages exist in a strange limbo between the world of matter and the shadow realm of antimatter. They're refugees from annihilation, temporarily safe in their electromagnetic sanctuaries, carrying information about the fundamental structure of reality. These experiments represent humanity's most sophisticated attempt to commune with the universe's hidden twin. We're learning to speak the language of antimatter, one trapped particle at a time, hoping to hear echoes of the cosmic choice that allowed our universe to exist. The work continues around the clock, with scientists from around the world collaborating to push the boundaries of what's possible. Each successful trapping event, each moment that antimatter survives in captivity, brings us closer to understanding our own existence. As you drift toward sleep tonight, imagine those solitary antiprotons orbiting in their magnetic wells, survivors of the cosmic lottery that chose matter over antimatter. They carry within their invisible dance the memory of creation itself. In the morning, these same antiparticles might find new purposes, perhaps traveling to hospitals where they'll help doctors peer inside human bodies with unprecedented clarity. Close your eyes and imagine you could shrink down to the size of a blood cell and travel through your own body. You would see rivers of red blood flowing through vessels like underground streams. You would witness the steady rhythm of your heart pumping life through corridors of tissue. You would discover landscapes of organs working in harmony to keep you alive. But some parts of this inner world remain hidden, even from the most powerful microscopes. Diseases can lurk in shadows. Injuries can hide in places where normal light cannot reach. Organs can whisper their troubles in languages that doctors struggle to understand. This is where antimatter becomes medicine's most gentle detective. In hospitals around the world, doctors use a remarkable imaging technique that depends on the same particle-antiparticle annihilation that shaped the early universe. It's called PET scanning, which stands for positron emission tomography. The positrons in this technique are the same antimatter twins of electrons that we've been exploring throughout our journey. The process begins with a special kind of sugar that's been modified in a subtle but important way. Normal sugar contains carbon atoms, but this medical sugar contains a slightly different version of carbon, one that's unstable and wants to transform into something more stable. When these unstable carbon atoms decay, they don't simply disappear. Instead, they transform into ordinary carbon while releasing a positron, a tiny spark of antimatter that begins a brief but meaningful journey through your body. Think of these positrons as microscopic messengers carrying glowing letters through the postal system of your bloodstream. They travel with your blood, following the same paths that nutrients and oxygen take as they nourish your cells. Different parts of your body use sugar at different rates. Your brain, which thinks constantly, consumes sugar rapidly to fuel your thoughts and dreams. Active muscles burn sugar to power your movements. Healing tissues use extra sugar to rebuild themselves. Cancer cells, unfortunately, often consume sugar even faster than healthy cells. As the medical sugar travels through your body, it accumulates wherever cells are working hardest. The busier the tissue, the more sugar it absorbs, and the more positrons are released when that sugar's carbon atoms decay. These positrons don't travel far. In the warm, dense environment of your body, each antimatter particle survives for only a few millimeters before it encounters an electron, its matter twin. When they meet, something beautiful happens. They annihilate in a gentle flash of pure energy, creating two photons of light that fly apart in exactly opposite directions. These photons are special. They carry exactly the same amount of energy and travel at precisely the speed of light. Most importantly, they emerge from the exact spot where the antimatter and matter met, the place where your body was using the medical sugar most actively. Around your body, arranged in a perfect circle, sensors wait patiently for these light signals. They're like a ring of electronic ears listening for the whispers of annihilation. When two sensors detect photons arriving at exactly the same time from opposite directions, they know that somewhere along the line connecting them, a positron found an electron. By collecting millions of these coincident signals, computers can reconstruct a detailed map of where antimatter annihilations occurred throughout your body. This map reveals the hidden geography of your metabolism, which parts of your body are working hard, which are resting, and which might be troubled by disease. The resulting images are like glowing paintings of your body's inner activity. Active brain regions shine brightly as they consume the medical sugar and create antimatter sparks. Your heart glows with the steady rhythm of its muscular contractions. Healing bones show bright spots where new tissue grows. But PET scans can reveal more than just normal body functions. Tumors often appear as bright spots because cancer cells typically consume sugar faster than healthy cells. Infections show up as glowing areas where immune cells battle invading bacteria. Brain disorders become visible as patterns of unusual activity or darkness. The antimatter in medical PET scans is completely safe for patients. The positrons exist for such brief moments and in such tiny quantities that they pose no danger. Each positron lives for only microseconds before finding its electron partner and transforming into harmless light. In fact, you're naturally radioactive to a small degree. Your body contains trace amounts of unstable elements that occasionally release positrons even without medical intervention. The PET scan simply adds a controlled amount of this natural process, directing it to reveal specific information about your health. The beauty of this technique lies in its gentleness. Unlike some medical procedures that require cutting or inserting instruments into your body, PET scanning simply watches the light show created by antimatter annihilation. It's completely painless and reveals information that would be impossible to obtain any other way. Scientists continue to develop new versions of medical antimatter tracers. Some attach positron-emitting atoms to molecules that are absorbed specifically by certain types of cells. Others create traces that reveal how well organs are functioning or how effectively treatments are working. Researchers are even exploring ways to use antimatter for cancer treatment. The idea is to attach positron-emitting atoms to molecules that cancer cells prefer over healthy cells. When the antimatter annihilates, it would release energy precisely where the cancer is located, potentially destroying tumor cells while sparing healthy tissue. The irony is profound. Antimatter, the universe's choice for what not to become, now helps us understand and heal our bodies. The cosmic accident that eliminated most antimatter from the universe left behind just enough natural processes to create the medical positrons that illuminate our inner landscapes. Every PET scan represents a conversation between the largest and smallest scales of existence. The same physics that governed the first moments after the Big Bang now helps doctors peer inside your beating heart. The annihilation process that nearly emptied the universe of matter now reveals the hidden geography of human health. As you rest tonight, remember that antimatter continues to play a healing role in hospitals around the world. Patients receive gentle injections of medical sugar, and positrons begin their brief journeys through bloodstreams, carrying information about health and disease to the sensors that surround them. The light created when these antimatter messengers find their electron partners travels outward at the speed of light, carrying maps of human metabolism to computers that paint glowing portraits of inner wellness. In this way, the universe's rejected twin becomes medicine's most insightful friend. But antimatter's story extends beyond healing and scientific discovery. It invites us to imagine what might have been, what kind of universe could have existed if the cosmic coin had flipped the other way. Imagine for a moment that you could step through a cosmic doorway into a parallel universe, one where the tiniest decision in the first fraction of a second after the Big Bang went the other way. In this mirror cosmos, antimatter won the ancient battle, and matter became the ghost that haunts the edges of existence. In this antimatter universe, everything would look remarkably familiar at first glance. The laws of physics would work exactly the same way. Gravity would still pull objects together. Light would still travel at the same speed. Energy would still equal mass times the speed of light squared. The fundamental rules that govern reality would remain unchanged. But look closer, and you would discover a world built from the universe's opposite twin. Anti-stars would shine in the anti-sky, their nuclear hearts fusing anti-hydrogen into anti-helium, releasing the same warm light that bathes your world. These stellar furnaces would forge heavier anti-elements in their cores, anti-carbon, anti-oxygen, anti-iron, scattering them through space when they died in brilliant anti-supernovas. Antiplanets would orbit these anti-stars, their surfaces carved by anti-erosion, their atmospheres swirling with anti-weather. Anti-moons would pull anti-tides across anti-oceans, where anti-life might have learned to swim, to crawl onto anti-land, and eventually to think anti-thoughts under anti-constellations. The strangest part is that an anti-person living in this mirror universe would experience everything exactly as you do. They would feel the warmth of their anti-sun on their anti-skin. Their anti-eyes would see the same colors in the same rainbow after anti-storms. Their anti-heart would beat with the same rhythm of life that pulses in your chest right now. This anti-person would have no way of knowing they lived in an antimatter universe. To them, their matter would simply be matter. Your universe would be the strange one made of exotic antimatter. The concepts of normal and backward, real and reflection, would be completely reversed. If you could somehow observe this antimatter universe from a safe distance, you would see something remarkable. Despite being built from opposite particles, it would evolve in parallel with your own cosmos. Anti-galaxies would spiral through anti-space. Anti-civilizations might build anti-telescopes to study their anti-sky, never suspecting that across an impossible divide, matter beings were contemplating their existence. The most beautiful aspect of this mirror universe is how perfectly it would complement your own. If you could somehow combine the two cosmos, bringing matter and antimatter together, they would annihilate completely, transforming into pure energy that would outshine all the stars that ever existed. But this perfect symmetry raises profound questions about the nature of existence itself. If antimatter universes are possible, why don't we observe them? If the laws of physics treat matter and antimatter equally, why does our corner of reality seem to prefer one over the other? Some scientists propose that antimatter universes might actually exist, separated from ours by barriers we cannot cross. Perhaps when the Big Bang occurred, it created not one universe but two, a matter universe and an antimatter universe, that began expanding away from each other faster than light could travel between them. In this scenario, both universes would be equally real, equally valid, equally deserving of existence. Somewhere across an unbridgeable cosmic divide, antimatter stars might be warming antimatter worlds where antimatter life dreams antimatter dreams about the nature of reality. Other theories suggest that the entire universe might contain equal amounts of matter and antimatter, but they exist in separate regions so vast that we simply haven't encountered the antimatter domains yet. Like two different continents on the same planet, matter and antimatter territories might coexist without ever meeting. The boundary between such regions would be spectacular beyond imagination. Where matter and antimatter domains touched, continuous annihilation would create walls of pure energy stretching across space. These cosmic boundaries would shine brighter than entire galaxies, powered by the endless transformation of mass into light. But perhaps the most intriguing possibility is that antimatter universes exist in dimensions we cannot perceive. Just as a shadow on a wall hints at three-dimensional objects we cannot see directly, the tiny amounts of antimatter in our universe might be shadows cast by vast antimatter realms existing in parallel dimensions. String theory, our most advanced attempt to understand reality's deepest structure, suggests that the universe might have far more dimensions than the three of space and one of time that we experience. In these hidden dimensions, entire antimatter realities might flourish, forever separated from our matter-dominated cosmos by barriers of geometry itself. The contemplation of antimatter universes teaches us something profound about the nature of existence. It reminds us that reality might be far stranger and more wonderful than we can easily imagine. The cosmos that seems so solid and permanent might be just one possibility among infinite alternatives. Every breath you take, every heartbeat, every thought exists because of an ancient cosmic choice that we still don't fully understand. You are not just a collection of atoms arranged in a particular pattern. You are a representative of matter's victory in the universe's greatest competition, a living symbol of existence itself. Yet in imagining antimatter worlds, we also discover the deep democracy of physics. The laws of nature show no inherent preference for matter over antimatter. The equations that describe reality remain perfectly balanced, perfectly fair, perfectly symmetric. If antimatter had won the cosmic lottery instead of matter, the universe would be just as rich, just as beautiful, just as capable of creating complexity and consciousness. This symmetry suggests that existence itself, rather than any particular form of existence, is what the universe fundamentally supports. Whether built from matter or antimatter, reality seeks to know itself through whatever patterns of complexity it can create. As you drift toward sleep tonight, let your imagination wander across the cosmic boundary that separates what is from what might have been. Picture antimatter galaxies spinning in anti-space, antimatter worlds orbiting anti-stars, antimatter consciousness contemplating the same mysteries that occupy your thoughts. In your dreams, you might visit these impossible realms where everything is simultaneously identical to and opposite from your own experience. You might walk on antimatter ground under antimatter sky, breathing antimatter air while your antimatter heart beats with the same rhythm of wonder that connects all conscious beings to the cosmos they inhabit. The universe that might have been exists forever in the realm of possibility, a perfect mirror reflecting the profound mystery of why anything exists at all rather than nothing, and why you are here to ponder the question. Tomorrow you will wake in the matter universe that chose you, carrying the memory of antimatter dreams that whisper of realities beyond the boundaries of what can ever be directly known.